Welcome to this explainer. You know, on the surface, the trajectory looks exactly like your standard 15-day high school physics simulation. It's got kinematics, thermodynamics, orbital mechanics, the whole shebang. But hiding just beneath that standard math curriculum, well, it's actually a psychological thriller. It's this brilliant pressure cooker environment designed to test how human beings make decisions when literally everything goes wrong. Okay, let's dive into this. The premise of the simulation puts these students in mission control for the Athena IV deep space mission. They're tasked with navigating a crewed spacecraft to a metallic asteroid called Vesta 7. But here's the catch. The goal isn't just to get the math right. The real objective is to put students under such intense pressure that their natural cognitive flaws surface. It forces them to experience and hopefully overcome the exact same biases that cause real-world experts to fail. To build that pressure, the simulation relies on incredible scale and total isolation. The Athena IV crew is a staggering 140 million miles from Earth. And that distance isn't just a fun fact. It creates a massive communications delay. Every single piece of telemetry data the students get is already over 12 minutes old. I mean, imagine the frustration of teenagers dealing with internet lag, but this time billions of dollars and virtual human lives are on the line. If something goes wrong, they can't just fix it in real time. They have to predict, prepare, and act based on a reality that is already in the past. And to make matters even more difficult, the 6 students on a team are completely isolated in their roles. You've got the navigation officer tracking velocity, the power systems engineer watching the fuel, life support monitoring radiation. You get the idea. But the brilliant part is that no single student sees the complete picture. They only have their own fragmented pieces of the puzzle. To keep the crew alive, they absolutely must synthesize these conflicting priorities and communicate perfectly.
All right, let's look at Section 1, the core mechanic, subtitled Burn Windows. This is where doing the math meets having the guts to actually act on it.
Throughout the mission, students face 3 critical burn windows to correct their trajectory. It's a strict 3-step sequence. First, they have to do the rigorous physics calculations to prepare. Second, they have to either commit to the burn right then and there or choose to wait for more data. And finally, they have to live with the consequences of that choice. This sequence forces calculated risk-taking, making the trajectory the only patience framework simulation with this specific pressure cooker mechanic. Moving on to Section 2, the real enemy. 6 cognitive biases. Now, what's really interesting about this slide is the simulation's massive twist. The true antagonist isn't deep space, and it definitely isn't the physics. The real enemy is the students' own minds. You see, the curriculum secretly weaves 6 specific cognitive biases into the daily data releases just to trap them. The very first trap they encounter is information bias. On day 5 of the simulation, teams realize their trajectory is drifting. They actually have enough data to calculate a course correction, but their numbers have an 8% margin of uncertainty. Navigation will naturally beg for just one more day to narrow that margin. But the math shows that any correction within that 8% variance will still safely save the ship. So the simulation is testing a really crucial distinction here. Are the students waiting because they genuinely need more information to make a safe decision? Or are they just using the request for more data as a psychological crutch? Because let's face it, deciding is uncomfortable and waiting feels like you're being careful. Think about how often we do this in our own lives, waiting for one more report just to delay an uncomfortable choice. But in this simulation, waiting is just decision avoidance, and it's going to cost them massive amounts of fuel later on. Let's move to and see how this builds into the next trap, the Semmelweis reflex. On day 7, right after teams finally perfect their complex trajectory plans, a massive solar flare warning comes in. Preparing for the flare means powering down systems and completely ruining their beautiful, hard-won plan. The natural reflex for a lot of smart students is to just dismiss or minimize the warning entirely, simply because accepting it means they'd have to change everything. Next up is Section 3, Falling for the Decoy, focusing on the Day 10 ethical choice. As we reach the approach phase, the simulation shifts gears from purely technical math to a profound ethical dilemma, balancing pure science against crew safety. Students are presented with 3 orbit options. Option Alpha prioritizes science, but it costs a lot of fuel and hits the crew with high radiation. Option Beta prioritizes safety, using less fuel and keeping radiation low, but you sacrifice the science data. And then there's Gamma. Gamma looks like a nice compromise, right? But
But if you actually run the numbers, it is objectively the worst choice. It costs almost as much fuel as alpha, but delivers far less science, and it's way less safe than beta.
So why is it there? Gamma exists for one reason, to trigger the decoy effect. It's a trap option designed specifically to make alpha look much better by comparison. The real choice is between alpha's science and beta's safety, but the presence of the weaker gamma option distorts the student's evaluation. It traps the smart teams who think comparing options relative to each other is the exact same thing as objectively evaluating the hard data.
Which brings us to Section 4, the 30% trap, Day 13's gravitational assist. By the end of the mission, teams usually think they've got this whole thing figured out. And that is exactly when the simulation actively punishes teams who learned the wrong lessons about risk.
And this brilliantly illustrates the trap. On Day 13, teams are offered a gravitational assist shortcut home. Choosing this shortcut saves them 11 days and almost 5% of their fuel. It boasts a 70% chance of success. Sounds great, right? But it also mathematically guarantees a 30% chance of a catastrophic trajectory error that strands and loses the crew. And it completely ignores the fact that a totally safe, standard alternative route exists. So why would brilliant physics students choose a 1 in 3 chance of literally killing their crew? Because of scope insensitivity. A 30% failure rate just doesn't emotionally feel like nearly 1 in 3 crews dying. It just feels like a small number compared to 70%. This failure to emotionally register the profound proportional magnitude of the risk causes otherwise highly intelligent students to treat it as a perfectly acceptable gamble. The simulation is contrasting two very different things here. Back on Day 5, the data showed all outcomes were safe, demanding calculated boldness based on evidence. But Day 13 proves that acting impulsively against a 30% catastrophic risk, especially when a completely safe option exists, is just pure recklessness. Even if the teacher rolls a die in class and the shortcut happens to succeed, it doesn't change the fact that the underlying reasoning was horribly flawed.
Finally, Section 5, Process over Outcomes, the pedagogical payoff. This brings us to the absolute genius of the final grading rubrics on Day 14.
So the crucial point is this. Students are evaluated purely on the quality of their reasoning, not the dashboard outcomes of their mission. A team that carefully analyzed the data, recognized their biases, and still ended up with poor metrics will actually score significantly higher than a team that blindly guessed, made reckless decisions, and just happened to stumble into a lucky survival. This is a concept called productive failure recovery. During the final debrief, teachers use this exact prompt with the students. What is the cost of defending a decision rather than adjusting? Teams have to look back at the precise moments their choices started failing. Did they rationally analyze the new data and pivot? Or did they dig their heels in to protect their egos, explaining away the bad news just because they were already committed to a plan? It's an absolutely incredible way to learn. And honestly, it makes you wonder, how often do we fall for these exact same cognitive traps in our own high-stakes environments? Think about it. If your team rolled a success on a 30% catastrophic risk, would your reasoning actually survive the debrief? The trajectory proves that having the right data just isn't enough if you don't understand how your own mind is processing it. Thanks so much for joining me for this explainer on the patience framework and these fascinating concepts. Keep questioning your assumptions, and I'll catch you next time.